Today we are talking about rational functions as x, or the limits of rational functions as x approaches infinity. Let's jump right in. So we're going to start with this function here, negative 14x over 7x plus 4. Now, remember, as x is approaching infinity, that means we're approaching a very, very large number. So if we're looking at a very, very large number, billions and billions, however large you want to go, that 4 becomes fairly insignificant. So for our purposes, as we're approaching infinity, we kind of disregard the constants at the end of a function. That's the term without a variable attached to it. So we're going to plug in a large number for x, and we'll see what we can come up with. Well, let's pick 100,000. So we're going to pick 100,000. We put that value in, and what do we do with this? Well, if we were doing any other function or any other fraction, we would cancel out those 100,000. So we're left with negative 14 over 7, which is negative 2. So that's our limit, negative 2. But that's not just our limit, that's also our horizontal asymptote. Horizontal asymptotes are when your x values approach very, very large numbers. And then we have our vertical asymptotes. We can find a vertical asymptote just by setting the denominator equal to 0. So we set 7x plus 4 equals 0, and we solve for this and find that x is equal to negative 4 over 7. So let's see what this graph looks like. As you can see, this graph is similar to a reciprocal function. We have our horizontal asymptote here at negative 2, and we have roughly our vertical asymptote in here at negative 4/7. That one's a little bit harder to get in there, but our negative 4/7. Great, let's look at another function. Okay, here we are with 5x squared plus 8x minus 3 over 3x squared plus 2. Again, the negative 3 and the 2 are fairly insignificant as we approach infinity. So we've got our the remaining portion of that function, 5x squared plus 8x over 3x squared. Now we could pick another value and just plug it in and say let's try and cancel and work this out. But we can also remember, if you find the limit of a similar function, that will give you the limit of your existing function or your original function. So what we can do is we can do our canceling beforehand, and we're going to multiply by a value that will of 1 that will give us, or simplify this a little bit more to make our calculations a little bit easier. So all we're going to do is we're going to multiply by 1 over x squared over 1 over x squared. So that's again 1, but as we distribute this, what we'll see is our x squareds will cancel out for our 5 and our 3, and our 8 will be left with 8 over x. Now why do we do that? Well, if we pick a really big number now for x, we know 8 over a really big number is going to be practically 0. So we're left with 5 plus 0 over 3. And now that's really easy. We have our limit of 5 over 3. So our horizontal asymptote is going to be 5 over 3, and our vertical asymptote is going to be when our denominator equals 0, when x equals 0, when we set our denominator equal to 0. And if we do that calculation, I'll let you do that on your own, you will actually see that there is no vertical asymptote. And let's confirm that with our graph. So here our graph shows that there is no vertical asymptote, but there is a horizontal asymptote. Now you might be thinking, wait a minute, horizontal asymptotes, this thing is crossing our function right here. Yes, it is, but when we're talking about asymptotes, we're actually talking about what the graph is approaching at the extremities, that it never crosses. So it's approaching these values, but it never touches them. So as we get very, very large, as we get very, very small, we're approaching that value, but never actually getting there. So this is your horizontal asymptote. Let's look at another example. This example is a little different than the previous ones because you can notice that the highest power in the numerator is different than the highest power in the denominator. So we've got 11x plus 2 over 2x cubed minus 1. So we're going to get rid of that 2 and negative 1, and we are going to be left with 11x over 2x cubed. Using the same idea that we did in the previous example, we're going to multiply by a specific value of 1 that will make this a little bit easier for us to work with. So we're just going to multiply by that highest degree. Let's do 1 over x cubed. So when we do 1 over x cubed, that leaves us in the numerator with 11 over x squared, and in the denominator 2 over 1. And we know as 11 over a really big number squared, that's going to be approaching 0, so we have our limit at 0, which is our horizontal asymptote as well. Horizontal asymptote is, what's going on here? Horizontal asymptote is 0. And our vertical asymptote is, if we were to work this out, and you can do this on paper, and you set that denominator equal to 0, you'd get the cubed root of 1 over 2, and when you rationalize that, you get a vertical asymptote of cubed root 2 over 2. Let's take a look at that graph real quick. Okay, so here we see we've got our vertical asymptote at the cubed root of 2 over 2, and we can see that as we go to our extremities, we are indeed approaching 0. So this is matching up with what we just found as well. Alright, we got one more example. Okay, and our last one that we're going to look at today is 2x squared minus 3 over 7x plus 4. Now, look at this one. This one's a little bit different as well. This one has got the numerator now has a higher degree than the denominator. So this, again, the negative 3 and 4 are going to be not significant when we start looking at really large numbers. And we are still going to find our limit of a similar function, which is going to be 2x squared over 7x. We'll take, again, this time not the highest degree in the numerator, but we're still going to take the highest degree in the denominator to see what happens here, because we want to get rid of that denominator, or we want to get rid of that down there. So we're going to multiply by 1 over x, and that's going to give us 2x over 7. Now, the 2 and the 7, as we get really large, again, those can kind of cancel out, and they become not as significant. So if we take a really large number, we multiply it by 2, and we just divide by 7, that doesn't mean a whole lot, because it's still a really large number. So what we end up with is our value as x approaches infinity is still infinity. Now this is something completely different, because we're left with a variable when we start canceling everything out. We're left with 2x. Everything else we came down to constants, and we were able to figure that out. So let's take a look and see what happens if we take this to the negative infinity. Well, if we go through the same process, we're going to find 2x over 7. That 2 and the 7 go away, and we're going to negative infinity. Well, this is a little different now. Of course, we're still just looking for the limits. We're not necessarily looking for the asymptotes. We're looking for the limits. But we can see that these limits are different. So that graph is going to look a little bit different as well. Let's take a quick look at that. So what this ends up giving us is actually a graph of, it's called a slant asymptote. So you end up having a value, I'm drawing this a little backwards here. You have a slant asymptote that your values approach. So it's not really a horizontal asymptote. Now we're not going to concern ourselves with the slant asymptotes at this time, but that's something to keep in mind when you have a variable left in the numerator. The denominator we can still see, as we've set that thing equal to 0, we would have a vertical asymptote here at negative 4 over 7. So what does all of this mean? Ultimately, what this means is if we are trying to find the limit of a rational function. We just divide by the highest degree or the highest power in the denominator to help us simplify the fraction, and that, or the rational function, and that will give us the limit or the horizontal asymptote, or I guess we could also say the slant asymptote as well. So, hope that helps, and we'll talk to you in the next video.